In this video, we'll start studying combinatorial proofs. So the particular type of combinatorial proof we will study is what is known as double counting. So to motivate this, we'll go back to the problem of outfits from one of the previous homework assignments. So Zaina had 12 shirts and 5 shorts or 7 skirts to pick from. And suppose two group members got two different formulas. One person found theirs by first considering the number of ways Zaina could pick a top, and then the number of ways Zaina could pick a bottom part of her outfit. And since her bottom part of the outfit consists of either skirts or shorts, she has to make a choice, and so it's 5 plus 7 ways to pick the bottom part of the outfit and 12 ways to pick the top. Therefore, by the multiplicative principle, this should be the answer. On the other hand, suppose someone came up with this route. First, they broke the problem up into cases. First, consider all outfits involving shorts. Well, given an outfit involving shorts, you have to pick a top and you have to pick a pair of shorts. So there's 12 times 5 options. On the other hand, case 2, suppose you picked a skirt. Well, the number of outfits involving skirts involves picking a top and then picking a skirt. So that many options. Since these cases are disjoint, the sum gives you the total number of outfits. This actually gives a direct proof of the distributive property of multiplication over addition, by the way, because you know that these two numbers are the same. So one way you know that's by knowing multiplication is distributive, but another one is because we've just proven that these two formulas give you the same answer to the same counting problem. And since the size of a set never changes, that must mean these two numbers have to be equal. So in general, you found two formulas, A and B. So these are numbers, some sort of sum of products of some sort of nonsense. They both represent the size of some set you're interested in counting. Then, assuming no one made a mistake, it must be the case that A is equal to B. And so combinatorics like this. So for the group work exercises, I'll usually give you a counting problem and then two parts where you have to compute a formula one way and then another, and then the conclusion is that the two formulas are the same. However, usually for mathematicians, we go in the reverse direction. The puzzle is you're given A equals B, and you want to actually find the counting problem and the argument that proves it. But that's usually a little more abstract, so we won't go that far. But for the videos, we will. So here's the first example of a double counting problem that pops up. It's a known fact that we often assume without proof that n choose k is equal to n factorial over k factorial times n minus k factorial. But where does that formula come from? Well, if you multiply both sides by k factorial, you get this expression, and when you divide out that n minus k factorial, you get this expression on the right-hand side. And so this equality is equivalent to this one. And the advantage of this equation is it's clear that both sides are integers, because you're multiplying an integer by an integer, and here you're multiplying a bunch of integers together. And so here is an identity, and we want to prove it by finding a set and showing that that size of that set is given by both formulas by enumerating the elements of that set in two different ways. In other words, two different students came up with different arguments. In this case, our job is easy because we already know that the formula on the right-hand side is the set of k permutations of the integers 1 through n. In other words, sequences of length k with numbers, entries 1 through n with no repeats. We've already shown previously that that satisfies this formula. On the other hand, another way we could have picked a k permutation is by first picking the set of elements in the k permutation and then putting it in some order. So for instance, an example of a k permutation of 5, so in the case n equals 5, k equals 3, you want a sequence of length 3. Well, first specify the 3 elements that are going to appear in your sequence. There's n choose k, or 5 choose 3 ways to pick out those k elements. Now you have to put them in some order, k factorial possible ways. It's k factorial because you have no repetitions. And so once you've done that, you've now created a K permutation. And you can see all possible K permutations come from this construction, because all K permutations consist of some ordering of K distinct elements. And so, therefore, this product, K factorial times n choose K, is also the size of capital A sub nk. And so this is a second counting argument, and previously did the first one. And so we found two different formulas describing the size of the same set, so the two formulas must be equal. And now it's just algebra. If you divide both sides by K factorial, you get the famous formula for binomial coefficients we normally teach in grade school. But now you know where that formula comes from. So this is kind of like using completing the square to prove the quadratic formula. You now understand why this is the correct formula. This also goes along with the intuitive proof. So the intuitive proof is that the way you pick K elements out of a set of size n is you take all things in an order, and you take the first K things on the list. But then you realize that the remaining things could have been in any order and you get the same result, and the first K things could have been in any order and you get the same result. Anyhow, this is a proof of this fact. So something along the same lines, let n, k, and m be positive integers, then it proves out this product of binomial coefficients is equal to this product of binomial coefficients. And one way to prove it algebraically is to just write down the formulas for binomial coefficients and do cancellations. But for combinatorics purposes or discrete math, we don't like that approach. We like to have some sort of puzzle, some sort of counting problem that we solve two different ways. One way getting this formula, another way getting this formula. And then we can say these things are equal. The reason why we do this type of thing is because there are counting problems out there where we don't have nice formulas on either side, but we have a recurrence relations or something more complicated. In other words, cases where you can't just use algebra to show the result. So intuitively, how could we think about this? Well, look at the left-hand side. You're picking K objects out of N objects, and then you're picking M out of N minus K objects. Well, the K and the N here are related, so, after you've picked K things out of a hat containing N objects, you have N minus K things left behind. So you could think of this as picking M of the remaining things. If you think about that, you suddenly start to see what the problem might be. The problem is picking teams, A and B. To make things a little more entertaining, I'm just going to call them dodgeball teams. You're going to pick two sets, A and B. Order matters here, because we had to make these choices in sequence, so order matters. And the point is that A union B is a collection of the integers 1 through n, so the n things in our hat. The size of A is k, and the size of B is m, and we require the intersections to be disjoint. And so what we see from the left-hand side, now we go backwards. Let's just assume you gave this problem to someone, and one of the students in your group, say Sarah, says, well, let's solve this problem by first picking A. There's n choose k many ways to pick the set A. Then you must pick the set B. Since B is disjoint from A, the elements of B come from 1 through n, take away A. So B is a subset of this set. This set has size n minus k. B has size m. There are n minus k choose m ways to pick the set B. And so by the multiplicative principle, the number of pairs satisfying this problem, the number of AB satisfying these constraints, is n choose k times n minus k choose m. But now you talk to your other partner and John says, no, that's not correct. This is how I did it. First, I picked the union. I picked the collection of elements in A union B. And there's n choose k plus m many ways to do that, because A union B has size k plus m, because these two sets are going to be disjoint. Now, once I've done that, I pick the B team as a subset of A union B. Since A union B has size k plus m, I have K plus M, choose M many ways to pick the set B. And once I've chosen B, A is uniquely determined because A is the leftovers. It's this set difference. And so A has size K here, exactly as we want. And so John's answer gives this right-hand side. But you see, since you're counting, assuming neither of them made a mistake, and neither of them did in this case, what we can conclude is that these two formulas must actually be equal. John and Sarah managed to calculate the same set two different ways, so the two numbers are the same. So therefore, for all n, k, and m non-negative integers, these product of binomial coefficients is equal to this product of binomial coefficients. And in general, that's what a double counting proof consists of. Although, again, like I said, for the group work, I will often be giving you something in this form, and then one part involves computing something like Sarah's answer, step by step, how to make the choices. So you get one formula, and then the second part of the problem involves a different set of steps, calculating the formula a different way, giving you a different formula, and then the conclusion is that the two formulas have to be equal. And therefore, you will have proven a combinatorial identity.